So today, I'm going to talk about modeling the panchromatic acids from a semi-analytic model called DustSH. When I talk about panchromatic, I don't know what panchromatic means, right? But what I mean is like the far ultraviolet to far infrared acids. And I'm interested to see like how better dust treatment, because like lots of model neglected dust. So I want to see like how better dust treatment improve for modeling of the acid from far UV to far infrared. So here I'm showing the pure stellar acid in the blue line and see how the dust absorb those light in UV to near infrared and re-emit the light in a longer wavelength. The semi-analytic model that I use is the modification of DarrenSage. I make improvement in the chemical enrichment model and also in the dust treatment. So DustSH include the infall process, it include like cooling of the hot gas to the interstellar medium, then formation of the molecular clouds, then the star form in the molecular clouds. And now the chemical enrichment model like depends on the stellar evolution. So low mass stars will expel their metals in the AGB phase, while high mass stars will expel their metals in the supernovae. We also have like supernovae 1A. These metals can later condense into dust, and the dust grows in the dense molecular clouds and destroyed by the shocks generated by supernovae. The model also implemented feedback, both by supernovae and AGN. So feedback is like it brings out materials from the interstellar medium out to the halo and even out of the system, which we call the ejected reservoir in the model, where dust can undergo further destruction by sputtering because it's really hot there. Then we have like the reincorporation process that reincorporate the material from the ejected reservoir back to the halo and back to the SM and so on. So what I did now is taking the star formation history and metallicity history from the model, so like millions of galaxies from the Millennium simulation, and use that to assemble the stellar population synthesis from Brugeot and Charlotte 2003. So this, like the bottom part of this shows the spectra of the single stellar population, so a population of stars with the same age and metallicity. And using this history to assemble that, we can get the pure intrinsic spectra of all of the galaxies in DustSH. Now, because I also have the physical dust properties from the model, then I can use that to compute the attenuation parameters. So I explore several recipes to transform the dust properties to the attenuation parameters. This is showing the work from Eagle, from Treyford 2020. Then the total absorbed light by dust is re-emitted to the infrared, and I use several infrared emission. I tried several infrared emission, and this shows like the overall acids. Different lines here shows the different model variants. So this is the different model variants, like that's all I. On the first part is where I vary the attenuation prescription. So basically different attenuation transformation. In my default model, I use the Eagle conversion. I also tried one from Sommerfeld 2012, which used the UV luminosity function as the main constraint. So it's more empirical. And as the test, I use a single attenuation parameter set from the default values of Charlotte and Fall 2000. So in this, in the dotted blue line, it will show like single attenuation parameters for all of the galaxies. Right, so let's see the luminosity function at redshift 0. At far UV, the cyan solid line is showing the pure intrinsic spectra. So we have like enough star formation. So this is redshift 0. And we see that the dashed dotted blue line is the single attenuation parameter. It's not enough to match the observed data set. So our dust mass dependent attenuation recipe works better here. this is showing the optical to near infrared, and we see like the same trend. So consistently using the attenuation tied to the dust mass, it's like match the observed data set better. And we see how the effect of dust decrease with increasing wavelength as expected. So basically at K-band, all of the model variants sit at the same place because it's mostly stellar emission. Now in near to mid infrared at 3.6 to 4.5 micron, it's still the same as K-band, all of the model like sit in the same place, but we see how starting at like 5.8 micron, the dust made a difference because this is where the emission from dust starts to also not negligible in the emission. There is a huge tension here at 8 micron. This is like a very complicated wavelength because it is where the contamination of AGN also peaks. So to explore like how the AGN changed their luminosity function, I played with the AGN parameters in the Dale infrared templates and see like by increasing the AGN fraction, it helps to solve the tension. But here's like only like the toy model because in the model, I haven't really touched the AGN properly. So this is just to explore how the model, like the default model, should be treated as a lower limit in this mid-infrared waveband because we use the AGN fraction as 0 for the default. Now at the far infrared where dust emission is dominating, we see here like, so again, the dashed dotted blue line here is the single attenuation parameters. And because it has the least absorption in the ultraviolet, of course, it will have the least emission in the far infrared. So again, using dust-dependent attenuation recipe consistently works across wavelength. Then I tried model with different infrared template with different parameters. So the Dale model here is more empirical. So I did lots of conversion from the physical dust properties to the infrared templates, while the Safazadeh model here is derived from the hydrodynamical simulation. So that's the black solid line, and the Dale is the dashed green line. And it shows that the dust model, where we can just choose the template based on the dust mass parameter, works better in our model. How many? Okay, I still have 3 minutes. Okay, so that's our results in the redshift 0. Now moving to the high redshift. So I have to make a disclaimer that dusty stage is only constrained using observation from redshift 0. So this is like production. I just wanted to see how the model behave at high redshift. This showing the K-band, which represent the stellar mass function at the model. We see here that starting at redshift 1, there is a like excess of faint galaxies in the model. This is a problem also happen at lots of semi-analytic model, and it might be solved by using alternative time scale for the reincorporation process of the gas to back to the halo and back to the ISM. Now, this is another interesting problem. It's like the obscuration of star formation rate at high redshift. So at far UV here, we see that like up to redshift 0, our model like attenuation still works okay in matching the observation, but at redshift 2 and redshift 3, our pure, like the cyan line here is like the pure unattenuated model just match the observation right. So no dust attenuation in the model is needed to bring it down. And that's probably the problem of like the obscured so the model is constrained by the cosmic star formation rate history, right? And there is a bias there that's only like bias to the unobscured star formation rate, which can happen to the model. So this like confirms that problem. And the total infrared luminosity functions, because we have not enough obscuration of star formation rate at UV, then it translates to the total infrared. So we still have to improve the model at high redshift, but the takeaway message that I want you to take from this is like, dust deserve better treatment in simulations. That's it. Thank you.